So, good morning, everyone. I'm Dr. P. Sarala, an associate professor from Mallareddy Engineering College, and I'm going to explain you the basics of electromagnetic fields. So, here the electromagnetic fields consist of both electrostatics as well as the magnetostatics. So, electrostatics can be defined as the study of electrical charges, and the magnetostatic is the study of about the magnetics. Okay, so here we are going to see the two fundamental laws which are governing these electrostatics. So electric field have their sources in electric charges. So the electric charge may be a positive charge or a negative charge. So here we are going to see the two fundamental laws which are governing the electrostatic fields. So here the two laws are Coulomb's law and Gauss law. So Coulomb's law is here first we go with Coulomb's law. And the Coulomb's law is applicable in finding electric field due to any charge distribution. And the Gauss law is easier to use when the distribution of symmetrical. So first we go with Coulomb's law. So here the Coulomb's law is determined by using a force of charges. So there will be a force exerted on charge. So this force can be an attractive force or a repulsive force. So when there will be an attractive force, so whenever the two different charges, that is when positive charge and negative charge are placed in a very small distance, then there will be a force of attraction between these two charges. If negative charge and come closer with the another negative charge, then there will be a repulsive force. So here the Coulomb's law is determined by having a force. So here the force is attractive force. The force is attractive force if charges are in opposite sign. So force is also proportional to the product of charges, that is Q1 and Q2, along the lines of joining them. So that Q1 and Q2 are opposite sign charges, and the force is proportional to the product of the two magnitude of the charges. And also the force is inversely proportional to the square of the distance between them. So here the force is proportional to the charges and the force is also inversely proportional to the square of the distance. So that is given as F is proportional to Q1, Q2 by R12 square. So here it is the square one, so it is R12 square. Or if we remove this proportionality constant, then the force is equal to Q1, Q2 by R12 square. So what is this proportionality constant? Okay, so the unit of constants can be determined from Coulomb's law. So here K is nothing but 8.987 into 10.9 Newton meter square per Coulomb square. So K is normally expressed as 1 by 4 pi epsilon naught. So here the K value is 1 by 4 pi epsilon naught. Then what is this epsilon? Epsilon naught is nothing but the permittivity of a free space. Okay, so here we are going to calculate the force. The force is nothing but F is equal to 1 by 4 pi epsilon naught Q1 Q2 by R square. Okay, so here so I'm going to write it. So here force is equal to 1 by 4 pi epsilon naught. Okay, Q1 Q2 by R square. So this is the Coulomb's law, which is going to tell about the force between two charges, that is Q1 and Q2. Okay, so now let's go with, see, the equation for the magnitude of Coulomb force between two point charges Q1 and Q2 in a vacuum is given by F12, that is the force from Q1 to Q2 by 4 pi epsilon naught R12 square, where Q1 and Q2 are the magnitude of the charges Q1 and the Q2 is magnitude of charge Q2, which is expressed in coulombs. Force F12 is electrical force acting on the charge Q1 due to charge Q2. Okay, here 1, 2 represents on 1 due to 2. So R12 is the distance between the point of charges Q1 and Q2 in meters. And epsilon naught is the permittivity of free space, that is Coulomb square per Newton meter per meter square. The 1 by 4 pi epsilon naught is a Coulomb constant. So the direction of the force F12 is determined the sign of the charges. The force is attractive if the charges have opposite sign, the repulsive if the charges have the same sign. Okay, so here there will be the direction of the force is explained with the help of whether the charge is positive or the negative. So if the charges are both opposite sign, then there will be a force of attractive. If their charges are both same sign, then we get the repulsive force. Okay, so now let us go with vector form of the Coulomb's law. So let us see here, there is a Q1 charge and there is a Q2 charge. So now both are, how these are both are positive charges, right? So both are positive charges. So the force will be repulsive force. See, the force is moving over here and this force on Q2 is moving over here. So the distance between this is R12. So this is, the R12 is explained a unit vector, that is the distance between Q1 and Q2. So the distance, the vector is nothing but which is having the direction as well as the magnitude. So here the direction of force is given and the magnitude is nothing but the distance. And here if we see two charges, that is positive charge and there is a negative charge, right? So both the four charges are different sign. So there is the force of attraction exists between these two charges. So here in the vector form, how can we express F12 is equal to Q1 Q2 by 4 pi epsilon naught R12 square R12. So this R12 is a vector which is having the magnitude as well as the direction. So now, if we see force from many charges, so till now we have seen only two charges. So we just directly given Q1, Q2. If we are having from many charges, here we are going to explain with respect to superposition theorem. That is, we are adding all the forces, a vector sum of all the forces, which will give the equivalent force. Okay, so now here let us see, there is a positive charge. So the force is acting on positive charge due to this negative Q2 charge, Q3 charge and Q4 charge. Okay, so let us see the F21 and F21, both are attractive one. Okay, F31, this is also attractive force, and here FQ4, which is a repulsive force. So force on charge is vector sum of all forces from all charges. Okay, so here now let us go with Coulomb's law, that is 1 by 4 pi epsilon naught Q1 Q2 by R12 square R12. So here the force can be attractive or repulsive and the force is inversely proportional to R square and the force is very strong over here and only relevant relatively local squares. So now we go with electric field. So what is an electric field? So the field around the electric charge is consisting of electric field. Normally we know that the charge around the area around the charge where there is an influence of that charge. So that area is called as electric field. So here they prefer to the of an object producing a field and another objects interacting with that field. So this is they like to think. Okay. Now physicists did not like the concept of action at a distance. So if by Coulomb's law, so at a distance, if we go on increasing the distance, what happens? The force becomes very weak. So the Coulomb, so here there is an field developed against across around the charge, which is called as electric field. So what is this an electric field? So this electric field is defined as force acting on a test particle divided by the charge. So see here the equation for the electric field. Electric field is equal to the F by Q naught. So here F is nothing but the force and Q naught is the charge. So here let us see, this is the charge and the force acting. So the electric field is also acting along the force. So thus electric field from a single charge. So the electric field is taken for a single charge, that is 1 by 4 pi epsilon naught Q by R square, where the R is the vector. So here electric field is acting along the distance, along the direction of force. So now let us go with electric field of a single charge. So here let us take, this is a single charge. Okay, this is the test particle. Okay, so here there is an Q naught, here Q naught, here Q naught, and here Q naught. So the electric field is acting along the direction of the other charges. The electric field is defined everywhere, even if there is no test charge is not there. So now charged particles in an electric field. So here the positive, so this is the electric field for the positive charge as well as the negative charge. So this is the direction of field along the force. F is equal to Q. And here minus Q. So minus Q is nothing but negative charge. So negative charge, the force is acting here, not along this direction. So it is acting along the other direction. So F is equal to Q here. So vectors and scalars in the electric field. So electric field as a vector field. So here the electric field is one of the example of a vector field. So this electric field is also having magnitude and direction, right? So here a field is defined everywhere, whether it is a vector or a scalar. So a vector field has direction as well as size, that is the magnitude. So the electric field has units of Newton per Coulomb. Newton is a force unit, Coulomb is a charge unit. So here we are going to get Newton per Coulomb. The electric field is having the units. Okay. So here, and we go with representation of electric field. So here, it would be difficult to represent the electric field by drawing vectors. Those direction was the direction of the field and whose length was the size of the field everywhere. So here I already explained that the electric field is in the direction of the force. Okay, so see here, this is the test charge. So the electric field is over here. So the direction is in the direction of the force. So if we take so many test charges, then the field direction will be in this way. So instead we choose to represent the electric field with lines whose direction indicate the direction of the field. So now we move away from the charge, the density of line decreases. So as we move away from the charges, what happens? The field, so field gets weakened. So the lines of charges, lines of force, lines of flux is going to be decreased. So the density of lines going to be decreased. So these are called as electric field lines. So now let us go with how we are going to draw the electric field lines. So the lines must begin on positive charge. So the positive charge, from the positive charge, if we take the positive charge over here, the line is going to begin from the positive charge and it is going to move through an infinity. So if we're going to take the negative charge, so the lines must end on a negative charge. That is, the lines, see here. This is the positive charge. If we keep a positive charge over here, the electric field lines are going to start from the positive charge and end at an infinity level. And if we take a negative charge, then the lines are going to end to the charge which are coming from the infinity level. So here, if we take a positive charge and a negative charge, so the lines are starting from the positive charge and they are going to end at the negative charge. So always the lines of forces tries to move from positive charge to the negative charge. So the number of lines leaving a positive charge or approaching a negative charge is proportional to the magnitude of the charge. So here the number of lines are proportional to the charge. So the electric field lines cannot cross each other. Okay. So here the electric field lines cannot cross each other. So here the electric field lines are showing starting and ending. So field is not zero here. So here the field is zero because there is no field over here. And so electric field lines in this way, there is a positive charge, then it is going to end at an infinity level. So now see here, positive charge and a negative charge. So it is going to end at the negative charge, leaving from the positive charge. So electric field lines, so here rho is the density which is proportional to Q by 4 pi r square. So electric field is 1 by 4 pi epsilon naught Q by r square. So E is proportional to rho. So interrupting the electric field lines, the electric field vector E is at a tangent to the electric field lines at each point along the lines. The number of lines per unit area through a surface perpendicular to the field is proportional to the strength of the electric field in that region. So here also we are going to use the superposition theorem for the electric field. So if we are having more number of charges where the field is acting on them, then we are going to add the field same like that, like the force we are adding. So electric flux. So what is electric flux? So for a constant field perpendicular to, so here there is a field. So there is a electric flux lines defined as E into A. So that is field into the area gives the flux lines. So here the electric flux is non-perpendicular. So here electric flux is normally electric field is nothing but number of flux lines per area. So here flux is nothing but E into A cos theta. So the electric flux is relation to field lines. So here E into A. So rho is nothing but density is proportional to E. So here field line is given as number of flux lines is proportional to the flux.